Machine learning, ML, is a branch of artificial intelligence, AI, that enables computer systems to learn from data and improve over time without being explicitly programmed. Through the creation of algorithms, machine learning constructs mathematical models that predict outcomes based on historical data, integrating statistics and computer science. These algorithms and models can identify patterns, make predictions, or generate insights from large and complex datasets. ML is essential because it allows us to tackle problems that are difficult or impossible to solve with traditional programming methods, particularly those involving large volumes of data or complex patterns. Its relevance in AI stems from its ability to automate tasks, optimize processes, and enable systems to adapt and improve based on experience. ML algorithms power a wide range of applications, including personalized recommendations, predictive analytics, autonomous systems, and natural language processing. By leveraging ML techniques, AI systems can perceive, reason, and act in ways that simulate human intelligence, driving innovation and advancements across various industries and domains. Machine learning, ML, a subset of artificial intelligence, AI, specializes in developing algorithms and models that learn from data to enhance their performance over time. ML aims to empower machines to derive insights from data, thus improving their ability to produce accurate outputs. In contrast, the broader objective of AI is to engineer intelligent computer systems capable of addressing intricate problems akin to human intelligence. Machines learn by ingesting input data into a machine learning algorithm during the training phase, thereby constructing a logical model based on learned patterns. This model is then utilized to process new data, enabling the generation of predictions or decisions. Through this iterative process, machines continuously refine their understanding, contributing to their ability to learn and adapt. These techniques empower machines to discern meaningful patterns from data, make informed predictions, and enhance their performance progressively, thereby driving advancements in intelligent systems and applications. The journey of creating an effective ML model commences with data collection, a critical phase wherein information is gathered from various sources like Excel, Access, and text files. The quality, diversity, and quantity of this data are pivotal in shaping the functionality of ML models, underscoring the significance of meticulous data acquisition. Subsequently, the focus shifts to data preparation, where the collected data undergoes rigorous cleaning to ensure its quality and reliability. This involves handling missing values, removing duplicates, and rectifying inconsistencies and errors to furnish accurate input for training the ML model. With the data primed and refined, attention turns to model training, where the selection of an appropriate algorithm is guided by the specific problem and data characteristics. The training dataset serves as the playground for the algorithm, which iteratively adjusts its parameters to minimize the disparity between predicted and actual outputs. Following model training, the next step is model evaluation, employing a separate test dataset to gauge its effectiveness. This evaluation phase provides insights into the model's performance on unseen data, offering valuable feedback on the chosen algorithm's efficacy. Finally, performance enhancement takes center stage, delving into metrics such as accuracy, precision, recall, and F1 score to gain a comprehensive understanding of the model's performance. This iterative process of data collection, preparation, training, evaluation, and enhancement forms the cornerstone of ML modeling. Machine learning, ML, applications span across numerous sectors, revolutionizing processes and driving innovation. In healthcare, ML powers medical image analysis to detect anomalies, aiding in diagnosis and treatment planning by automatically identifying abnormalities in medical images like X-rays and MRI scans. In finance, ML is utilized for stock market prediction, fraud detection, and customer relationship management, CRM, enhancing decision-making, minimizing financial risks, and optimizing customer interactions. E-commerce and marketing leverage ML for recommendation systems, customer segmentation, personalized marketing, and demand forecasting, improving customer experience and optimizing business operations. Natural language processing, NLP, enables ML-driven chatbots, virtual assistants, sentiment analysis, summarization, and text classification, automating customer service, analyzing textual data, and extracting insights from text. Additionally, computer vision employs ML for object detection, image recognition, facial recognition, image captioning, and video analysis, enabling applications such as biometric authentication, surveillance, and activity recognition. These applications highlight the transformative potential of ML across diverse industries, driving efficiency, enhancing decision-making, and unlocking new opportunities for businesses and society. Machine learning, ML, encompasses three main types: supervised, unsupervised, and reinforcement learning, each categorized based on the nature of learning and the availability of labeled data. While supervised learning involves training a model on labeled data to make predictions, unsupervised learning discovers patterns and structures in unlabeled data. Reinforcement learning, on the other hand, teaches an agent to interact with an environment to maximize rewards. Semi-supervised learning merges aspects of both supervised and unsupervised learning, harnessing the power of labeled and unlabeled data. The choice of ML technique depends on the problem at hand and the characteristics of the dataset, with different techniques being employed individually or in combination to achieve the desired outcome, exemplifying the versatility and adaptability of ML in addressing diverse challenges across various domains. Supervised learning is a foundational approach in machine learning where models learn from labeled data, comprehensively mapping input features to corresponding output labels. In this paradigm, the model analyzes patterns within the provided examples to establish a relationship between input data and target labels, subsequently enabling it to make predictions on new, unseen data. It encompasses two main types: classification, where the model predicts categorical labels, and regression, where it predicts continuous numerical values. Popular algorithms in supervised learning include logistic regression for binary classification tasks, decision trees for both classification and regression, random forests for ensemble learning, support vector machines, SVM, for classification, and linear regression for regression tasks. For instance, in email spam detection, a supervised learning algorithm analyzes labeled email datasets, learning to differentiate between spam and non-spam emails based on features like sender, subject, and content. Similarly, in medical diagnosis, supervised learning models are trained on labeled patient data, discerning patterns in symptoms and test results to predict the presence or absence of particular diseases. Supervised learning's versatility extends across various domains, from predicting housing prices to classifying images, making it a cornerstone of data-driven decision-making and predictive analytics. Unsupervised learning in machine learning is a powerful approach where models learn patterns and structures from unlabeled data without explicit guidance. This methodology is invaluable when labeled data is scarce or unavailable, enabling the discovery of underlying relationships and insights within datasets. Two prominent techniques within unsupervised learning are clustering and association. Clustering algorithms categorize data points into groups or clusters based on similarity, with each cluster representing a distinct category. A notable algorithm is k-means, which partitions data into k-clusters by minimizing the within-cluster variance. For example, in customer segmentation for an e-commerce platform, K means can group customers into segments such as frequent buyers, occasional shoppers, and bargain hunters based on their purchasing behavior. Association analysis uncovers relationships among items in a dataset, often employed in market basket analysis. The a priori algorithm is a widely used association mining technique that generates association rules indicating the likelihood of item co-occurrence in transactions. For instance, in a grocery store, a priori can identify associations like customers who buy milk are likely to purchase bread, informing inventory management and marketing strategies. These unsupervised learning techniques, alongside their algorithms, play pivotal roles across various domains. Reinforcement learning, RL, in machine learning revolves around an agent learning to make sequential decisions in an environment to maximize cumulative rewards. Unlike supervised learning, where models learn from labeled data, RL learns through trial and error feedback. Key components include the agent, which takes actions in the environment, receiving rewards or penalties based on its decisions. The agent's objective is to learn a policy that guides its actions to achieve the highest cumulative reward over time. For instance, in training an AI to play a video game, the agent interacts with the game environment, making decisions like moving or jumping, and receives rewards, points, accordingly. Algorithms like Q-learning, deep Q networks, DQN, and policy gradient methods are utilized to optimize the agent's decision-making policy. RL finds applications in various domains such as robotics, where it can train robots to perform tasks autonomously, finance, for optimizing trading strategies, and healthcare, in optimizing treatment plans. Reinforcement learning exemplifies the concept of learning through exploration and exploitation, enabling agents to tackle complex problems in dynamic environments. Linear regression is a fundamental algorithm in machine learning used for predicting continuous numerical values based on input features. It assumes a linear relationship between the input features and the target variable. The algorithm aims to find the best fitting line that minimizes the difference between the actual and predicted values. In a very simpler term, it is a foundational tool used for making predictions based on input data. Imagine you have a dataset with pairs of input-output values, like the number of hours a student studies and their corresponding test scores. Linear regression helps you find the relationship between these variables by fitting a straight line through the data points. This line represents the best approximation of how the output, test score, changes with changes in the input, study hours. Once you have this line, you can use it to predict future outcomes based on new input data. Linear regression is like a simple yet powerful calculator that learns from past examples to make educated guesses about what might happen in the future. Logistic regression is a type of classification algorithm in machine learning used to predict the probability of a categorical outcome. Despite its name, logistic regression is used for classification tasks rather than regression tasks. It models the relationship between one or more independent variables, features, and a binary outcome, typically coded as 0 or 1. Logistic regression uses the sigmoid function to transform the output into a probability value between 0 and 1. Instead of drawing a line on a graph like we did with linear regression, logistic regression draws a curved line that looks like a 92-92. In very simplistic terms, imagine you have a bunch of data points that represent different things, like whether an email is spam or not spam. Logistic regression is like drawing a line through these points to separate them into two groups. So when you give logistic regression some new data, it can tell you the likelihood of it belonging to one group or the other based on where it falls on that curved line. It's like a smart way of guessing whether an email is spam or not, based on patterns it sees in the data. So logistic regression in machine learning is essentially a way to classify data into different categories, based on the patterns it learns from training examples. It's a valuable tool for tasks like email filtering, medical diagnosis, and sentiment analysis in natural language processing. The K-nearest neighbors, KNN algorithm, is a straightforward yet powerful method in machine learning used for both classification and regression tasks. It operates on the principle of similarity. If an instance is similar to its neighbors, it's likely to belong to the same class or have a similar target value. For example, in a dataset of labeled fruits where each fruit is described by features like weight and color, KNN predicts the label of a new fruit by looking at the K closest fruits in the training set. If the majority of the K nearest fruits are apples, the algorithm predicts the new fruit to be an apple. Similarly, for regression tasks, KNN calculates the average of the target values of the K nearest neighbors to predict the value of a new instance. KNN is versatile and applicable in various domains, from recommendation systems in e-commerce to medical diagnosis and image recognition. Its simplicity and effectiveness make it a popular choice for many machine learning tasks, especially when the underlying data distribution is complex or nonlinear. K-means clustering is an unsupervised learning algorithm used to partition a dataset into K distinct clusters, where each cluster represents a group of similar data points. The algorithm begins by randomly selecting K data points as the initial centroids of the clusters. It then iteratively assigns each data point to the nearest centroid, forming K clusters based on the Euclidean distance between data points and centroids. After the assignment step, the centroids are recalculated as the mean of all data points assigned to each cluster. This process of reassigning data points and updating centroids continues iteratively until convergence, where the centroids no longer change significantly. For example, in a dataset containing customer information such as annual income and spending score, K-means clustering can segment customers into different groups based on their spending behavior, such as high, medium, and low spenders. K-means clustering is widely used in various domains for tasks like customer segmentation, image segmentation, and anomaly detection, enabling the discovery of hidden patterns within data. The decision tree algorithm in machine learning is a versatile tool utilized for both classification and regression tasks. It constructs a tree-like structure by recursively partitioning the dataset into subsets based on the most significant features. At each node, the algorithm selects the feature that maximizes the homogeneity of the subsets, typically measured by metrics like Gini impurity or information gain. This splitting process continues until certain stopping criteria are met, such as reaching a maximum depth or minimum number of samples in a node. The final nodes of the tree, known as leaf nodes, contain the predicted class labels or regression values. Decision trees find applications in various domains, including customer churn prediction, credit scoring, medical diagnosis, and predictive maintenance, owing to their simplicity, interpretability, and ability to capture complex decision-making processes in a transparent manner. Random forest is an ensemble learning algorithm in machine learning used for both classification and regression tasks. It operates by constructing multiple decision trees during the training phase and aggregating their predictions to make the final output more robust and accurate. Each decision tree in the random forest is trained on a subset of the training data and a random selection of features, thereby reducing overfitting and increasing model generalization. In classification tasks, the final prediction is made by taking a vote among the individual trees, while in regression tasks, it's calculated by averaging their predictions. Random forest finds applications in various domains, such as predictive maintenance, bioinformatics, finance, and marketing. For instance, in finance, it can be used to predict stock prices or assess credit risk, while in bioinformatics, it can predict protein-protein interactions or gene expression levels. A practical example of random forest is predicting housing prices based on features like square footage, number of bedrooms, and location, where each decision tree captures different patterns from the data, resulting in a robust estimate of house prices. You've reached a significant milestone in your journey toward mastering one of the most dynamic and influential fields within artificial intelligence. Throughout this course, you've delved into the depths of ML, uncovering its vast potential and practical applications across diverse domains. From understanding foundational concepts to exploring advanced algorithms and models, you've navigated ML's expansive landscape with determination and curiosity. However, true expertise in ML goes beyond theoretical knowledge. It requires hands-on practice and real-world application. As you embark on the next phase of your journey, embrace the opportunity to hone your skills through practical experimentation and problem-solving. Explore the endless possibilities of ML techniques and algorithms, and let your creativity and innovation shine as you tackle real-world challenges. Remember, the journey of mastering ML is as exciting as it is rewarding, and your dedication and perseverance will undoubtedly lead to success in this dynamic field. Best of luck on your continued journey in the exciting world of machine learning.